Hello everyone. Welcome to the week 7 of the live session for the course Differential Equation for Engineers, which is taken by Professor Srinivasa Manam from IIT Madras. And I am Priyanka Agarwal, a PMRF scholar at the Chemical Engineering Department, Indian Institute of Science, Bangalore. And I have been taking these tutorials, and today we are in week 7. So almost half the course is over, and now let's see what we have next. So in the lecture you have studied Bessel equations and how to solve them using Frobenius series and various properties of Bessel equations. So today we are going to do a quick review and then solve some problems related to Bessel equations and their functions of first kind specifically. Okay, so let's begin. Okay, we know that Bessel equation is of the form x square y double dash plus x y dash plus x square minus alpha square y equals to 0, where alpha belongs to some real number and alpha is always greater than equal to 0. So here x is either greater than 0 or x is less than 0, because x at equal to 0 is not defined. Okay, and we know that for this x equals to 0 is a regular singular point. Now using the Frobenius series solution, and we have done lot of examples on the series solutions. I hope it's clear to each and every one of you who has gone through this video or been there in the live session. So we can write yx as x to the power k summation n equals to 0 to infinity Cn xn, where x is greater than 0 and c naught is not equal to 0. So you know how to proceed with this Frobenius series. We substitute this yx into this, where we first differentiate and get y dash and then y double dash, and then solve for the coefficients of all the powers of x, and from there we get an indicial equation as well as a recurrence relation, which can be written in a series form. Now for this, as you have been demonstrated in the lecture, you know that in this equation you get the values of k as minus alpha and alpha, and here we are assuming that alpha is greater than equal to 0. Now saying that, we can write the general solution for this. General solution y of x is of the form c1 y1x plus c2 y2x, where 2 times alpha belongs to an integer, and we know that this y1x is a bounded solution, right? X equals to 0, and this y2x is unbounded. solution at x greater than 0. So this has already been taught in the lecture, so I'll not be uh, going in these details. Instead, I will discuss some examples based on what you have learned in the lecture. Okay, so you know that these y1 and y2 functions can be written as the Bessel functions, Jn, j minus n. These are Bessel functions of the first kind. Now, let's see a question where the Bessel function of the first kind is defined by the series Jn of x equals to summation r equals to 0 to infinity minus 1 to the power r over n plus r factorial r factorial x by 2 to the power 2r plus n. N is some integer. Okay, now use this definition to show that the generation function, which is e to the power x by 2 into t minus 1 by t, is equal to summation n equals to minus infinity to infinity t to the power n jn x, and n belongs to z. Now we have to solve this particular question. So for solving this, let's see the generating function first. Which is e to the power x by 2 into t minus 1 by t. Now this can be written as e to the power 1 by 2 x t minus, into e to the power minus 1 by 2 x over t, right? So once it is written in this form, we can write e to the power x in series form. So same thing we will do over here. We will write this as e to the summation k equals to 0 to infinity, where k is some variable just to run this series, 1 by 2 x t to the power k over k factorial, and similarly we can write the other series as summation n equals to 0, m is just index, right? So minus x by 2t to the power n over n factorial. So how has it come? We know that e to the power some function, if we have e to the power x, that can be written as some in this form, where this is x to the power k over k factorial, right? That's the series e to the power k. So we have written this in this form, and let's see how to solve further. So we can write it as this, both the summations together, k equals to 0 to infinity and n equals to 0 to infinity, then 1 by 2 xt to the power k into minus x by 2t into to the power n over k factorial n factorial. Right? Okay. So again, if we see, this can be written as k equals to 0 to infinity, m equals to 0 to infinity. So half and half can be combined. So first this is minus 1 to the power n, 1 by 2 to the power k plus n, x to the power k plus n, t to the power k minus n over k factorial n factorial. Right? Now there could be cases when k plus n is like k plus n is k minus n is positive or k minus n is negative. So we will see case by case. Let's say case 1 where power of t is positive. What would that mean? That k minus n is greater than equal to 0. So let's say k minus n equals to n, then k becomes n plus n, and k plus n can be written as then 2n plus n. So now this term e to the power x by 2 into t minus 1 by t becomes summation n equals to 0. So I am now replacing k by n, because if k is going from 0 to infinity and n is going from 0 to infinity, then n will also go from 0 to infinity. And since we are eliminating k from the entire equation, this particular equation, then we will replace k by n. So n equals to 0 to infinity and summation n equals to 0 to infinity. See, m remains here, minus 1 to the power n into 1 by 2 to the power 2n plus n, x to the power 2n plus n into t to the power n over n plus n factorial into n factorial. Right? Is it clear? Because see, this term has come as it is. Now this term k plus n is replaced by this 2n plus n. F k plus x to the power again 2n plus n, and k minus n is replaced by n, and k is replaced by n plus n. Okay, so this is now what we have. Now how can this be written? From n equals to 0 to infinity. See, t to the power n does not depend on n, so we can take it out. Now this is summation n equals to 0 to infinity, and then this is minus 1 to the power n, 1 by 2 to the power 2n plus n, x to the power 2n plus n, right? Into t to the power n we have already taken out, and then what remains here is n plus n factorial into n factorial. Now look carefully. This can be written as x by 2 to the power 2n plus n. Now look carefully at this particular term. What it is? Let's see the definition. Minus 1 to the power r n plus r factorial x power 2 to r factorial. So this is basically Jn, right? So this is actually your Jn of x. So you can write this as summation n equals to 0 to infinity t to the power n Jn of x. So we have seen this. Now let's solve for the other case. Here we consider that the power of t is some positive. Now here we consider that the power of t is a negative integer. So let's say minus n is now less than 0. So in this case what we will do, let k minus n equals to minus n, now which is less than 0. So therefore k can be written as n minus n, and k plus n can be written as 2n minus n. And similarly as we did in the case 1, we will solve for this case also. So this can be written e to the power x by 2 into t minus 1 by t, which is equal to summation k equals to 0 to infinity summation n equals to 0 to infinity minus 1 to the power n into 1 by 2 to the power k plus n into x to the power k plus n and t to the power k minus n. So this was there already. It's nothing new which I am bringing up. Right? Now how can this be changed now? Just we have to substitute this as k equals to n minus n. So this is now summation n equals to 0 to infinity summation n equals to 0 to infinity, and this becomes minus 1 to the power n. Combine these two, so this is x by 2 to the power k plus n. K plus n is now 2n minus n into t to the power k minus n is n over k factorial n factorial. Again k is what? N minus n factorial. N minus n factorial. Great. Now in a similar way, what can we do? Summation n equals to 0 to infinity, take t to the power n outside. Okay, k minus n is not minus n, not n, right? Okay, mistake. These happens. T to the power minus n, and then in the bracket we have this entire term n equals to 0 to infinity minus 1 to the power n x by 2 to the power 2n minus n over n minus n factorial into n factorial. Now if you look carefully at this, what is this term? J minus n, right? This is from the definition of the basic function itself. So this becomes n equals to 0 to infinity t to the power minus n j minus n. right? Here we know that n is greater than 0. If we can also write it as summation minus n equals to 0 to infinity. We replace minus n by n, 2 to the power n j n x, and this can be then written as n equals to 0 to minus infinity. It's basically the reverse way, minus infinity to 0. Right? Now, if you combine both the uh, cases 1 and 2, if you look at both of them simultaneously, you can write that e to the power x by 2t minus 1 by t can be written as summation n equals to minus infinity to infinity, right? T to the power n j x. So this is what we wanted to prove, and we have shown this. Okay, any questions? If not, then we will move to the next. I'll just take a pause so that if there is any question you can ask. Okay, looks like there is no other question. So we'll continue and we'll do a small question. Show that j0 dash x equals to minus j1 of x. Now for this you need to use the property of the Bessel function which has been taught in the class. So one such property is that if you differentiate x to the power minus n j n x, what you get is minus x to the power minus n j n plus 1 of x. Right? Now substitute n equals to 0. What you will get is d by dx of x to the power 0, 1, j0 of x equals to minus x to the power 0 again 1, j n plus 1, now 1 x 1. So what is this? j0 dash x equals to minus j1 x. Very simple, just making use of the properties which has already been derived in the lecture class. If you haven't visited that, please go and visit and you will understand it clearly. Now let's take a look at another question. Okay, so we have seen in the previous question how we get the generating function. So the generating function of the Bessel function of the first kind is something this. So this we have already seen in the first question, how to derive this generating function. Where n belongs to z. Now use this generating function to show that Jn of x plus y equals to summation n equals to minus infinity to infinity Jm of y into j n minus n of x. Now this is the question, and so let's see how to approach this. So we know that this is the generating function as it is given in the question itself. Jn of x. Now if we substitute x with y and multiply both e to the power in terms of x and into e to the power in terms of y, what we will get is e to the power x by 2 into t minus 1 by t into e to the power y by 2 into t minus 1 by t. See here, what we have to derive is some y function into some x function. So that is why with the generating function itself, we are once taking it with respect to x and then with respect to y and multiplying it. Now this you can write it as from the definition itself. Firstly, for this x case, t to the power k, jk of x, and then for the other case, you can write it as summation n equals to minus infinity to infinity t to the power n jm of y. Now, if you look clearly, it is e to the power 1 by 2 x plus y into t minus 1 by t. We have just added the powers of e and written it. So now this becomes summation k equals to minus infinity to infinity, and then summation n equals to minus infinity to infinity. This can be written as jk of x into jm of y t to the power k plus n. Now let n equals to k plus n. Okay, just write n equals to k plus n. Then what you will get is a to the power 1 by 2 x plus y into t minus 1 by t equals to summation n equals to minus infinity to infinity. Now we have to replace k everywhere with n, and this is summation n equals to minus infinity to infinity. Now k can be written as n minus n. So j n minus n of x into jn of y, and we have t to the power k plus n, which is n, and this becomes summation n equals to minus infinity to infinity. We can take it here because it does not contain any n. Summation n equals to minus infinity to infinity jm of y into j n minus n of x. Right? Now just look at this sum, what it is. So we can write this as e to the power 1 by 2 into n into t. Basically, this can be written as, let's say, instead of t minus 1 by t, or you can write it as some u,
Oh,
where u
ma'am,
is.
can I see one question, ma'am? I do not know the question.
Okay, so this is the question where the generating function of the Bessel function of the first kind is given, which is e to the power x by 2 into t minus 1 by t, and this is equal to summation n equals to minus infinity to infinity t to the power n jn x. Now, using this generating function, you have to show that Jn of x plus y equals to summation n equals to minus infinity to infinity Jm of y into Jn minus m of x. So, this is what you have to prove. Is the question clear now?
Yes, yes, ma'am, yes, ma'am.
Okay. Do I need to go through the solution once again, or it's clear?
Proceed, ma'am. Proceed from there.
Okay. So basically, starting from the generating function itself, we have first written e to the power this function and e to multiplied it with in terms of y, x and y, and then combined these terms, both both terms, and we are proceeding. So here now we see that this side we have x plus y, and this side we have simplified to this jm of y jn minus n x, which is one part of the uh, question which we have to prove. This is we have to prove, and we have already achieved this. Now if you see at this definition, if you consider this as some other term, let's say lambda, you can write this as jn of lambda, right? So this will become summation n equals to minus infinity to infinity t n jn of lambda, from this particular definition. And now you equate it to this, so you have this thing common both on both sides. So therefore you can write jn of lambda, which is actually jn of lambda is here x plus y. So I'll directly write it Jn of x plus y equals to summation n equals to minus infinity to infinity Jm of y into j n minus m of x. Any doubts in this?
Yes, ma'am. Proceed, ma'am.
Okay. Okay, we'll solve another problem, and which is the Bessel function of the first kind Jnx satisfies this Jn of x equals to summation p equals to 0 to infinity minus 1 to the power p n plus p factorial into p factorial x by 2 to the power 2p plus n. So basically this is the definition of the Bessel function. Now we have to show that Jn of x equals to 1 over root pi gamma function n plus 1 by 2 into x by 2 to the power n, where this is I, where this I is defined as 0 to pi cos x sin theta cos to the power 2n theta d theta. So this is the question which we have to solve. Okay, now to solve this, let's first look at this particular integral. Here we know that sin theta is an even function at around pi by 2, and cos square theta is also even function. So we can write I as 0 to pi by 2 and take 2 over here, 2 cos x sin theta cos to the power 2n theta d theta. Okay, now we can expand this cos function in series form. So 0 to pi by 2, 2, so this will become 1 minus x square sin square theta. So basically whatever is inside that becomes square over 2 factorial plus x to the power 4 sin to the power 4 theta over 4 factorial. So in expansion of cos, we see alternate minus and plus signs. Similarly, minus x to the power 6 sin 6 theta over 6 factorial and so on. And this is multiplied by cos 2n theta d theta. Now, if we look at this, we know that for 0 to pi by 2, 2 cos 2p minus 1x and sin to the power 2p minus 1x dx equals to beta function p and phi, and this can be written as gamma of p into gamma of phi over gamma of p plus phi. So this is already known. Now you have to make use of this and substitute in the I and simplify. So I equals to integral of 0 to pi by 2 to cos to the power 2n theta d theta. So basically in this you are just multiplying it with this, opening this term, when this becomes x square by 2 factorial integral 0 to pi by 2 to cos to the power 2n theta sin square theta d theta. Similarly, plus x to the power 4 by 4 factorial integral 0 to pi by 2 to cos to the power 2n theta sine to the power 4 theta d theta, and last term I'll write and so on. Now this can be simplified and written in terms of beta functions. Each integral can be written in terms of beta function. So this becomes beta of n plus 1 by 2 to 1 by 2 minus x square by 2 factorial. This becomes beta function of n plus 1 by 2 to 3 by 2, and similarly plus x to the power 4 by 4 factorial, beta function of n plus 1 by 2 5 by 2 minus x to the power 6 by 6 factorial, beta n plus 1 by 2, and this becomes now 7 by 2, and so on. Now beta function can then be expanded in terms of gamma function. So now this becomes gamma of n plus 1 by 2 into gamma of 1 by 2 over gamma of n plus 1, that is summation of these two, minus x square by 2 factorial gamma of n plus 1 by 2 gamma of 3 by 2 over gamma of n plus 2. Similarly, for all terms we can write gamma n plus 1 by 2 into gamma of 5 by 2 over gamma of n plus 3. And for this term, gamma of n plus 1 by 2 to gamma 7 by 2 to gamma of n plus 4, and so on. Now in all these terms, gamma of n plus 1 by 2 is common, and if we take that out, gamma of n plus 1 by 2, in first term we are having gamma of half over gamma of n plus 1. So we know that gamma of half can be written as root pi. Since gamma of half can be written as root pi. And gamma of n plus 1 can be written as, because we know that gamma of p can be written as some p minus 1 into gamma of p minus 1. So therefore gamma of n plus 1 can be written as n into gamma of n. N into gamma of n. Again, gamma of n can be written as n minus 1 factorial. Then other term x square over 2 factorial, gamma of n plus 1 by 2 is taken common, and then becomes gamma of 3 by 2. So gamma of 3 by 2 can be written as 1 plus 1 by 2. That means 1 by 2 into gamma. So gamma of 3 by 2 can be written as gamma of 1 plus 1 by 2. So from this we will get what? This will become gamma of 1 by 2 into 1 by 2. So this becomes 1 by 2 root pi. So we can write it as 1 by 2 root pi over gamma of n plus 2 will become n plus 1 factorial. And similarly, we can write for other terms. So this will become 3 by 2 into 1 by 2 root pi over n plus 2 factorial plus, so this is minus x to the power 6 over 6 factorial 5 by 2 into 3 by 2 into 1 by 2 root 5 over n plus 3 factorial and so on. Okay, is it clear till this point? Okay, so in this we can take now root pi as common again and n factorial also as common. So what will this become? I equals to gamma of n plus 1 by 2. Now root pi can be taken outside, root pi, and n factorial can also be taken as common. So now the first term becomes 1 minus, this is now x square over 2 factorial into 1 by 2 into n plus 1. Similarly, plus x to the power 4 over 4 factorial 3 by 2 into 1 by 2 over n plus 2 into n plus 1 minus x to the power 6 over 6 factorial 5 by 2 into 3 by 2 into 1 by 2 over n plus 3 into n plus 2 into n plus 1 and then so on. Okay. Now, how can we simplify this further? So, if we look at this term, gamma of n plus 1 by 2 into root pi over n factorial. Do you have any question?
No, ma'am. मतलब how to simplify this, ma'am? This bracket thing.
Yeah, that's what I'm showing. I'll show that how to simplify this. So 1 minus this becomes x square over 4n plus 1. This becomes x to the power 4 and this is 3 over 2 square, which is again 4. So you can write it as 4 into, now this is 4 factorial. So if you open this, this becomes 4 into 3 into 2 and at the top we have 3 into 1. This combined we have 4 over there, so this 3 cancels and then we have n plus 2, n plus 1 and in the other term we have x to the power 6 over 6 factorial. So again we have 6, 5, 4, 3, 2 and 1 and at the top we have 5, 3, 1. So this is 2 and now we have this n plus 3, n plus 2 into n plus 1. So if you see, these terms will get cancelled and everything we will be left is, we will be having will be in the power of, in the multiplications of 2. So now this becomes x square over 4 to the power 1 into 1 by 1 factorial into n plus 1. We can write it like this, it's the same thing. Then for this we can write it as x square over 4 square. So this term gets taken care of into 1 over 2 factorial n plus 2 into n plus 1. And similarly we can do for the third term also. Okay. Now if we just take this n factorial inside, what we have is gamma of n plus half 1 by n factorial minus x square pi 2 square to the power 1 into 1 upon n plus 1 factorial into 1 factorial. Similarly over here x square by 2 square to the power 2 into 1 over 2 factorial into n plus 2 factorial. Similarly the third term will be 1 over n plus 3 factorial into 3 factorial x square over 2 square to the power 3 plus and so on. So this is how we can write it. Now we see we can write this as x by 2 to the x by 2 square. This term is x by 2 to the power 4. This is x by 2 to the power 6 and like this. Now if we multiply by x by 2 to the power n in this, so we will get x by 2 to the power n I equals to root pi gamma of n plus 1 by 2, and what we have is 1 by n factorial x by 2 to the power n minus 1 by n plus 1 factorial 1 into 1 factorial x by 2 to the power of 2 plus n. Similarly, so basically we are trying to bring it in Bessel functions form. 1 over n plus 2 factorial 2 factorial x by 2 to the power, this becomes 4 plus n. So this is n, so this is becoming multiples of 2 and so on. So this entire thing, entire series can be written as summation n equals to 0 to infinity minus 1 to the power k over n plus k factorial into k factorial x by 2 to the power 2k plus n. Let's see, for n equals to 0, we have this, it's k, I'm writing series in terms of k. So for k equals to 0, the first term will be 1 over n factorial into x by 2 to the power n. Similarly, for k equals to 1, it will be minus sign n plus 1 factorial into this 1 factorial x by 2 to the power n plus 2. Now this we know is what? J n of x. So finally what we have got is x by 2 to the power n I equals to root pi gamma of n plus 1 by 2 Jn of x. So this is simplified to this, and then we can write Gn of x equals to I over root pi gamma of n plus 1 by 2 into x by 2 to the power n. And I already we know the definition. So this is what we have to prove, that Jn of x equals to I over root pi gamma n plus 1 by 2 x by 2 to the power n. So that's all for today's class. If you have any doubts, please ask.
Oh, yes, ma'am. Got.
Okay, great. Okay, so we'll close this session now. Thanks for attending and see you next week. Bye.